So my name is Jared Willard. I'm a PhD student at the University of Minnesota in the Department of Computer Science, working in the Kumar Lab and also with the USGS Water Resources Data Science team. And my talk is titled Process-Guided Meta-Transfer Learning for Predicting Temperature of Unmonitored Lake Systems. So Allison kind of already touched on the importance of lake temperature, but I'll just go through the main takeaways are that it's a very ecologically important variable. And this work in particular focuses on predicting lake temperature in one dimension, so temperature at various depths within the lake. So when predicting complex dynamical systems like temperature, which is thermodynamically driven, there are two primary classes of methods. The first being the traditional process-based models, process-driven models, which usually expressed through things like differential equations to explain emergent phenomena and mapping inputs to outputs, and then parameterizing missing physics, as many of you are probably already familiar with. And then on the other side of the coin, you have these data-driven models, which are all the rave these days, things like machine learning and more recently deep learning, which can take advantage of the millions and billions of sometimes data points available for modeling tasks as sensors get better and better. But in certain environmental systems, you don't have this massive data availability. So how can we apply things like deep learning, which have this extremely high data dependence often? So for example, for the USGS goal of modeling 100,000 plus lakes, over 95% of these actually don't have any temperature observations. So how can we apply things like deep learning, which have shown to predict lake temperature pretty accurately if you have a lot of data? But how can we harness these state-of-the-art data-driven or process-guided data-driven models when we don't actually have any data? So the key idea from machine learning that's important for tasks like these is known as transfer learning. So in this case, given an unmonitored lake system, we would want to find models from similar well-monitored systems, which we'll call source systems. And we aim to transfer these to a new lake that might not have any observations, and we'll call this the target system. And some of the biggest challenges in transfer learning, across disciplines are, what models do we transfer? What kind of models do we transfer? And from what systems? And in this work, we'll use ideas that use things like contextual lake attributes to determine, what is similar or what is transferable, which I'll talk about in later slides. So Allison already kind of talked about the idea of process-guided deep learning models, or also known as knowledge-guided or physics-guided. It goes by many names, but basically the key features are that these are deep learning models with temporal awareness. They have scientific theory-based feedback, and they also use pre-training to incorporate synthetic data from process-based simulations of lakes. And these have been shown to outperform process-based models in many situations, and also outperform data-driven models that have things like deep learning that have no knowledge of the underlying physics. So that's why we choose them as our candidate models. And these are candidate models for source models that would be transferred to target systems for prediction. So in terms of selecting the best models to transfer, we pose this as a meta-learning problem, which the idea is to build a model of models mapping differences in contextual attributes between lake systems and mapping those to model performance when you transfer a model to another lake. And so attributes can include things like maximum depth, surface area, among other things. And the idea is that in the model space here on the right, we would have source models built on every well-observed lakes that you would consider using as a source. And to build up the data to train the meta model. So this data to train the meta model consists of lake characteristics that aren't water temperature measurements, but things like depth and surface area, and mapping those to model performance here. And this data set is constructed by applying every source model to every other source lake. So if you had n sources, it'd be n times n minus 1 data points used to train the meta model. And ideally, you would learn systematically things like, lakes that have similar depths might transfer well, or lakes with surface area, similar surface area might transfer well, and things like that. So once the meta model is trained, given a new lake, you would use the lake characteristics of that lake to inform the meta model's prediction of which source models would be best transferred to that target lake. And more simply, just because this is a kind of complicated figure, we first use machine learning models, PGDL models from data-rich lakes. The meta learning model maps contextual data to performance. And then given an unobserved lake, we use contextual data to map it to PGDLs from similar systems. And then just in mathematical format, the response variable here would be the model error when transferring source to target. And that's built off the metadata that I talked about earlier. There's some examples here. And the model we choose to use for this regression task is gradient boosting regression. This outperformed several other methods like random forest regression, support vector regression, linear regression, and neural network when applied using cross-validation to the source model set. So in terms of selecting which meta features or lake characteristics to use, we use recursive feature elimination using cross-validation on the gradient boosting model. And we kind of just threw everything in the kitchen sink at it in terms of candidate meta features, but they're basically divided into 4 different categories. We have contextual lake data, so things like the difference in max depth between the source and the target system, difference in surface area, etc. And then the second category are observation statistics. So this would be things like, how many times was the source model observed to train, or how many times was the source system observed to train the source model? And, what's the average depth that they measure temperature at in that lake and things like that, which could be important for transferability. And then we have meteorological statistics. And then there's actually only one in this category, which is the process-based model simulation statistics. So this would be things like if you simulated the target and the source lake using a general lake model, what % of the years it's stratified in each case. And after performing this feature selection, we choose 8 meta features out of the 102, the most important being maximum depth and surface area. And then there are also a few more minor ones like number of source observations. So for the experiment of if this meta transfer learning can effectively predict lake temperature of unmonitored lake systems, we use data from the USGS data release process-guided deep learning predictions of lake water temperature. And we designate 145 lakes, mostly in the Minnesota, Wisconsin, but in the general Midwest area. We designate 145 of the most observed lakes as the source lakes to train the source models. And then we treat 305 other lakes as unobserved, shown in the dark blue here. And then we hold out another 2,000 or so lakes in light blue here for further analysis, but they're not actually usually well observed in that case, but it's shown more for scaling analysis. So the results of the meta transfer learning framework are compared against the PB0, which in this case is the GLM model, which has been expertly parameterized but has not been calibrated using any data. And the 3 rows here represent 3 different iterations of the meta transfer learning framework. The middle here, the middle row is going to be what I've explained so far mostly, which is using the meta model to select the top predicted PGDL source model and then transfer that to the target lake for each of the 305 lakes. And then the bottom row here is going to be a slightly expanded version of that, which instead of transferring just one source model, it transfers an ensemble of source models, which then combine all their predictions into an average prediction, which, if you're familiar with ensemble modeling, can improve prediction if you have diversity among different sources. And the top row here is also interesting because it's the exact same experiment as the middle row, selecting a single source, but instead of using 145 PGDL source models, we instead use 145 calibrated GLM source models. So these don't actually use any deep learning, but it's just, can we transfer parameters calibrated on well-observed systems and transfer them to unobserved systems? And is that predictable using a meta model? So we see that the best performance is in the bottom here. Using the ensemble model, we get an RMSE of about 1.92 degrees Celsius, as opposed to the existing process-based approach for predicting unmonitored systems, which has a median RMSE of about 2.6. And then the middle row here sits at about 2.18, and the calibrated GLM transfer is 2.4. So we do still see an improvement transferring the calibrated GLM models as opposed to just using the uncalibrated model from the target system itself. And I also just briefly highlighted the efficiency of the PGDL approach. Even in the ensemble case where you're selecting 9 models, it can predict 40 years of data, in a matter of seconds, which is often PGDL or deep learning models often execute faster than process-based models. So that's another advantage of that. So as a quick follow-up experiment, we wanted to compare how many observations are needed to forego the meta transfer learning framework and just use a PGDL model or another data-driven model from the lake itself. And so here we have an additional data point, which is this black line, which shows how well does the PGDL model do when trained on the data from the lake itself. So on the far left here, you would have a PGDL model trained on just one water temperature profile. And as we move along the x-axis, we increase the data and performance also improves, which is expected because it's a data-driven model. And then these green lines here, the light green is the PGDL MTL model, which is the best selected source PGDL model transferred to each of the target lakes, which we saw before the error was around 2.2. And then the ensemble approach would be 1.9 here in the dark green line. And we see that the crossover point for the ensemble model is actually a significant amount of data. Most lakes don't have this 35 or so observations available, and which is interesting. And the crossover point for the single source meta transfer learning model is around 5. And these are kind of the two extremes. So you have the meta transfer learning using no data, and then you have the PGDL using all the data. But you might imagine further work or different approaches that would use both. So you have things like model agnostic meta learning, or maybe you would fine tune a selected source model using data from the target lake, or similar approaches. But this is just a comparison of how well the PGDL does as you add more data to the unobserved prediction case. So I also want to highlight the generality of the meta transfer learning framework. It's not limited to lake temperature prediction. And as long as you have the minimum requirements, which are, you have contextual data for monitored and unmonitored data domains that could inform transferability, and you have, the monitoring data to actually train a data-driven model or calibrated process-based model, and then you have input drivers so that you could run the models on both the target and source system, this framework can apply. So in conclusion, for the studied lakes in the Midwest, PGDL MTL can accurately and efficiently predict daily lake temperature profiles, often less than 2 degrees RMSE for hundreds or thousands of lakes. And the meta learning can effectively learn from past experience to predict the best model for transferring to these ungauged systems. And going with the theme of this workshop, integrating scientific knowledge into machine learning shows promise for predictions of many societally relevant environmental variables, especially given the generality of this framework and many other approaches you will see described in this workshop. And that's my talk. Thank you.
Great, thanks, Jared. So actually, I have a question for you. This work that you're doing with your USGS collaborators and team seems very novel in the field of limnology in terms of using these ML models to predict characteristics of lakes that we don't know anything about. And I'm wondering if you wanted to say something about how you developed the methods. Is this something that your team sort of trialed and errored through, or is this something that you've seen used elsewhere and sort of adapted it to this project?
So this methodology kind of came out of, thinking about how we can predict lakes with no data, and then I kind of connected that to existing work in transfer learning. And then at first we just tried to transfer lakes, that were like nearby or that only looked at depth in a very like naive way, and all these approaches were insufficient. And then we kind of tried to pose it as a regression problem, like in the gradient boosting regression, but then that kind of opened the door to, what is this called in computer science actually? And then we discovered this entire wealth of work regarding meta learning, which actually hasn't been a hugely active field until very recently. And until then it was, back in the 90s when they were doing meta learning for model selection. But yeah, it's basically, to answer your question, mostly trial and error and connecting it to existing subfields.
Yeah, no, that's really neat. I think that's sort of important for, us who are thinking about trying to apply some of these methods, knowing the background of kind of how you got to where you are currently. So one more question for you from Slido. The question is, for matching these lakes, are you using any optical properties of the lake? So thinking about average color, lake color, or variation in color.
Yeah, so one of the candidate meta features, we did use water clarity as a candidate meta feature, but it didn't seem to inform transferability that much. That said, this approach hasn't been expanded, into like other regions where different features might prove important for different sets of lakes.
Yeah, and was that clarity static? Was there sort of one value per lake, or is that something that you left?
Yes. Okay. Yeah, the static value.
Okay. Interesting. Oh, great. Thanks, Jared.